Greetings everyone, this is Mr. Mall, and in this podcast I'm going to be reviewing the idea of current and also giving you an intro to what voltage is. So in the last podcast we talked about current, and current we said was the rate of flow of charge. So using that information, why don't you pause this video and try to answer this question. Alright, so when we look back at this, we've got 3 coulombs of charge being pumped out by the battery over the course of 5 minutes. So I've got 3 coulombs over 5 minutes is going to be my current flow. In circuit B, I've got 6 coulombs of charge pumped out by the battery in the course of 10 minutes. So even though there's more charge, it's taking longer. So when I can compare those rates, 3 divided by 5 and 6 divided by 10, we're going to find that the rate of flow of charge is the same for each. Okay, so it depends upon both how much charge, but also how quickly it moves through a cross-sectional area. Alright, today we're going to talk about voltage, and voltage technically, we'll give you a technical definition first, and then how it's going to apply to this class. Okay, so technically, voltage, and the symbol is delta V. Okay, so voltage is, and we'll see why it's a difference in a second, change in, is the difference in electrical potential electrical potential. Here's another thing that I don't have a definition for yet. Between 2 points in a circuit. When I say circuit, I meant continuous conducting path. Okay, so what is electrical potential? Electrical potential is defined as the energy per unit charge. So when I say potential energy, each little part of charge has some amount of energy associated with it. Its electrical potential is not the electrical potential energy, it's the energy that each individual unit of charge possesses, or stored there. So that's what electrical potential is. So practically in this class, sorry for all these little noises, we're going to be looking at voltage a little bit differently, and we're going to be thinking in terms of positive or negative. So a voltage is going to be like energy given to charges. By a battery. Okay, now when I'm thinking to be energy given to charges by a battery, I'm thinking of like a gravitational example of like an escalator or something. By having an escalator, giving the charge, storing energy in the gravitational field, or if there's a change in gravitational potential energy, voltage is kind of like this charge escalator that's giving charges energy. Okay, and maybe I'll even draw a little picture. So delta V is like energy given to charge by a battery. So I'm going to draw a little escalator here, and the book does something like this too. So here's my little charge escalator, and it's an escalator. Draw a little battery here. And here's my voltage source. It's giving energy charge, and a little escalator is kind of like giving, have an object getting more gravitational potential energy. I'm gaining energy as I go through this battery. Okay. A change in voltage could also be considered is like energy lost by charges as they flow through a conductor. So energy can be positive or negative. I can have a gain in voltage or a loss in voltage. And if I'm losing voltage, then my charge is no longer having the energy that it used to have. So I get up my charge escalator or my star stairs or my star ladder or whatever. I get to the top, and now it's like a little slide. So here's my charge going and going down the slide, and all that energy that it had before, like a gravitational potential energy, now that electrical potential energy is lost when I hit some kind of resistive element. So this could be like a light bulb or something, and I'm giving off energy. So my charge lost the energy. Well, it had to go somewhere, and the energy lost by the charge was, excuse me for a second while I get back to where I need to be. The energy lost by the charge was given off in the form of heat through the light bulb, or through a toaster, if that's what's taking the energy that my charge used to have, or whatever the resistive element is. So delta V is like energy given to charges, or energy lost by charges. And positive or negative voltage is probably going to correspond to one of those two things. SI unit for voltage is going to be the volt. And a volt is defined as 1 joule per coulomb. So the difference in electrical potential energy, so we said energy, or electrical potential was energy per charge, so joule per coulomb, energy per charge. That difference in energy per charge at the top of the slide versus my energy per charge at the bottom is known as voltage, and it's measured in volts. Okay, so this is what voltage is like, and I'm going to show you a little circuit here in a second. But let's look at, let's look at a circuit here. So this is, again, a PHET simulation here. And I'm going to set up a circuit. But before I kind of go along, so I just want to talk about something as a pre-lab discussion. So this is a voltage source. This is like an electron pump. And it's pumping charge through my battery. Okay? It's pumping charge through my battery. And as those electrons flow through, they can go in a certain path, and as they leave one end of the battery, one side of the battery, this is my positive end of the battery, this is my negative, my electrons flow through. Now, the conventional direction of current flow is actually the direction that the positive current would flow. So positive current is going to go away from the positive and towards the negative, even though the actual electrons are flowing in the opposite direction. All the math still works the same. So by convention, I is always flowing in the direction the positive would go, but the electrons are actually buzzing in the opposite direction. Anyway, as my electrons flow through, I can stick an ammeter in there, and the symbol A would how I could draw that in a circuit diagram, and I could measure the current flow. Okay. And then I could do a voltmeter. But in order to measure a voltmeter, I actually have to put it on either side of a resistor, or on either side of a battery. I could put a voltmeter as well. And the reason why we have to do this is because a voltmeter is going to measure the voltage, but that's an electric potential difference. And the only way I can have a difference is if I have two sides of a resistor before and after my charge has either gained or lost energy. So my electrons are buzzing through here at all the same speed, and as they're getting pushed, they can have more or less energy in the circuit depending upon if they've lost energy or gained energy from a resistive or some kind of source of voltage. So I have to put a voltmeter on either side of the resistor, thinking in the analogy of my slide, so I can see what that change in energy situation is going to be per unit of charge. And so that change in energy situation is going to directly correspond to the change in voltage, and I can measure the voltage drop across a resistor, but I've got to put it on either side. Okay. So explain why the voltmeter and ammeter must be placed where they are in the circuit, because the ammeter has to measure flow going through it, the rate of flow of charge. So an ammeter has to be placed in the circuit so that it can basically feel the charge flowing through it. A voltmeter has to be placed on either side of the resistor so that it can measure the change in voltage or the change in energy per charge before and after your charge experiences some resistor or some voltage source. Okay, so my last little thing I wanted to talk about was I just want to look at a simulation here really quickly. And I have got a lot of stuff going on my computer, so bear with me as I just try to get back up to get so I can see. I don't want that. Sorry. This is fine. Okay, I'm going to keep those. Okay, so I go back to my little simulation here. I'm not going to do that right now. Okay, so here's my circuit that I have here, and I've got my current flowing through it. And so there's my battery source there. I'm going to go ahead and remove that. I'm just going to throw an extra battery on here just for fun. And so my battery is acting as my electron pump. Okay, so it's pumping through. Now I added an extra battery, and you can see what that's doing to the, now my battery is giving even more charge to my electrons. So it makes sense that if they have more energy, that they're moving faster. So there they have, they're moving at some rate, 1.80 amps. Notice my little amp meter's right there. I pull out my little voltmeter here, and I want to measure the voltage. I would have to do so across a resistor. So I'm going to measure on one side of the light bulb and on the other side. Okay, so there we go. I'm going to switch the leads here. So there we go. I've got, it's measuring negative 17.97 volts. I can stick it on either side of the battery. Switch my resistor here. Okay, there I'm measuring positive 18 volts is my electrical potential difference. So I can measure the voltage across some ends of a resistor. I can measure across some part of the wire here. Okay, so looks like this wire has very low resistance, very small amount of voltage drop across the wire. I mean, some energy must be lost a little bit, but okay, so that's just kind of an example. And so when I look back at this here, you can think of those little batteries like climbing a ladder to a slide. And then you can think of a little resistor like a light bulb, or here's a resistor I could add in there. You can think of it like going down a slide as my particles are losing energy. But again, the particles are all moving at the same speed, and they're all moving in the same direction. The particles aren't getting used up, they're just getting recycled and energized. Okay, my particles are getting recycled and energized as they flow through this continuous conducting path as a result of this voltage source pushing those electrons. Alright, this has been a video on voltage, and I hope it's been helpful.